An atom can be as huge as an apple or paprika. Usually atoms are incredibly small. There is no microscope can show us an atom. The best is showing surface of atoms, not an atom itself. It's simply impossible. But an atom as huge as an apple can exist. Simply it's pushed in very unusual state. And this state is a gateway to the new generation of technologies. Unbelievably good sensors and even quantum computers. And I will overview this as well. Normally atoms are that small, so a million of them lined up will not exceed the thickness of a paper sheet. Just let that sink for a second. They are incredibly small. And can you imagine an object that expands that much, from that small to an apple size? Most stretchy thing I can imagine is an air balloon, but it expands 10 times in one direction, not even 100, moreover not a million. If you expand one direction a million times, what's even going on with the volume? To put that in perspective, it's like a cherry which was expand more than size of the Earth. Mind-blowing, my friends. And that's not just a bigger atom, it's a completely different condition of matter. That strange behavior, this system, is that interesting. It even deserved a Nobel Prize. Quite fresh Nobel Prize, to be honest. And the most interesting part is not even a huge size, sorry man. The most interesting is the behavior and what do they allow us to do. As for expansion, first we have to agree on what is expanding. And that's already a scientific problem. So, the paprika, what's the size of the paprika? The paprika has size of about 10 centimeters. But if we wanna measure it more precisely, that's 8 or 10 or I don't know. At least it has a solid border, and some objects do not have. For example, light beam. Where does a beam of light actually end? I have no idea. In fact, there are several ways to define it. If I take a cross-section of the beam, we get a distribution of intensity. And from that we can define its width in different ways. And despite those values can give you totally different numbers, all of them are correct. They are simply needed for different approaches. If you wanna build a laser pointer, you need one value, but if you wanna make a quantum computer, you probably take care of another one. The atom has the same problem. It's not a solid ball, it's a fuzzy cloud of electron probability. And there is no caliper can measure it. It simply has no solid border. Useless. Actually, the question, how do we estimate the size, brings us to the answer, how to even do it. Usually, we define size of the atom by how far it is from the other atom in a molecule. In other words, we pay attention to the bond length. That ends up with an immediate problem though. The length then depends on the type of the chemical bonding. It is on the type of the atoms which are around. That's messy. That's like I'm measuring my waist in winter clothes and several pullovers. But there is a way to measure it without any clothes, and then we have to use not chemistry but physics. To get a real definition of the size, we have to pay attention to the electron cloud. How do we understand it? In quantum mechanics, the electron is defined by its wave function. It's a mathematical object which tells you what's a probability to find an electron in a certain area in the space. And from that, we can conclude something objective, the mean radius. And it's pure math, so no guessing anymore, no blurry borders, no fuzzy clouds. Pure math. And this math reveals something fascinating. An atom has built-in volume knob. Turn it one way, an atom explodes in size. And there is a crazy part. This knob is not from 0 to 10, it goes to hundreds, thousands. It has actually no upper limit. There are surely some physical limitations, but the atom just grows. For the hydrogen atom, mean radius can be defined certainly according to the formula. Its core is just a combination of fundamental constants and some quantum numbers. And look at this N letter. It's our volume knob. And even though the other parameters are actually fundamental constants, I will show you how to change some of them. I promise you, do not change pi. So let's come back to N. What's actually N? It's a label of quantum state. If the electron is trapped by a potential gap, it forms a number of states, and N is simply enumerating them. It does not sound crazy. I am sure you all have seen those levels in real life. At least you have heard them. It's like a guitar string. You can pluck it to get a basic tone, but you also can excite a higher harmonics with more hums. More energy means more vibrations and more complex shape. Atom is quite same to the guitar string. They are also standing waves, but a bit more complex. Yes, they are quite different, but the basic concept is totally same. Coming back to digits, the energy itself is defined by surprisingly simple relation. As N grows, the energy levels go higher and higher. But they are not rising infinitely, they are getting closer and closer to some certain border, to the ionization energy. First huge steps of the ladder become paper thin at the top. And there is a hard limit, ionization energy. You cannot overcome. If you do, electron flies away. Actually, we can get incredibly close without crossing the limit. There are different levels, and if electron being on one state gets some extra energy, it can go from one state to another one. To change the state, electron has to get exactly the same energy as difference between those two levels. For the levels which are far away from each other, we can use light to give this exactly energy. For example, laser light, because it's monochromatic. Choosing wavelengths, in other words photon energy, we can tune precisely to the energy difference between two levels. Those two levels electron can jump between also have to fulfill certain conditions, so-called selection rules. Let's not focus on, let's say we choose only the proper pairs of levels. For the high levels, energy became that small, there is no light can give such small energy. So we have to use not even light but microwaves. And here's the trick, which allows us to make atom huge. When we pump energy into the atom, N grows, and because the mean radius depends on N as square, even a small portion of energy makes atom extremely huge. Think about this like a spacecraft. More energy you pump into your engines, the higher orbit you are getting. You are still tied to the Earth, but the loop you're circling is getting bigger and bigger. Actually, the mass is extremely close because gravitational potential and the electrostatic potentials are same, at least in shape. So you can make bigger and bigger loop till you are reaching escape velocity, or in case of atom, ionization energy. You are just a satellite on a really long leash. Think of it like a piano. When you hit a key, you are getting a specific note, C, D, E. And you can't really get a tone which is in between of them. Rydberg noticed that for the light emitted from atoms it works exactly the same. It does not emit a rainbow, it emits distinct specific wavelength. Not a rainbow, but specific wavelengths. He came up with a formula which predicts position of the lines with incredible precision. But there was a catch. The formula included the variable n, and he had no idea what does it mean. The only thing he was sure, it had to be an integer number. Surely he has seen n's not exceeding of 10's 15, but theoretically this n could be infinite. And that's exactly what we are speaking about. At the time, no one realized that n is actually number of state from the formula. Scientists have seen only a few levels, and no one expected it can go up to thousands. Today the states are called Rydberg states. They are named after the man who first described architecture of the atom. So coming back, how does it look like if we kick an electron in a more excited state? The world's records are insane. We have pushed atoms to the state number 100 100, 400 and even 1000, so it became 1 million times bigger. The growth was insane. N of 1000 doesn't make much sense itself. It's more like Guinness World Record. It will never deserve Nobel Prize. Yet in 2012 the Nobel Prize for research in this very topic was awarded. And they reached only N of 60. So what special did they do to deserve such much of attention, reaching only N of 60? And how did it pave the way to quantum computing and quantum spin? Think of me as a nucleus, and that's my electron. And that's a thin leash which is holding the electron. As higher energy is, as more far away the electron is. And then the leash is getting more thin and more fragile. When N is huge, it's not a leash anymore. It's a single thread of spider silk. One breeze, one knock, one sound nearby, it's already enough to demolish that state. Even to let the state to survive, we need already some special conditions. I haven't yet begun how to prepare this state, and moreover how to use it. In a normal room, the giant atom would not last a nanosecond. Tiny nudge, a tiny kick, and the leash snaps. The atom gets ionized, there is no Rydberg state anymore. Catastrophe. If you are standing in a crowd, you can't really spin it back around of you. It works this way, you see? I mean, it doesn't work. To do this, you have to be alone. I mean, truly alone. And for the giant atoms, it works exactly the same. Area nearby must be empty, almost completely empty. And in physics, we call it vacuum. To keep those giants alive, we have to give them a lot of space to do not interface with each other. For this, we need not a simply vacuum, we need an ultra-high vacuum. And that was the first challenge. Imagine social distancing, which we have had several years ago, but in an extreme shape. It's not keeping distance of 3 meters, not even one person in a room, not even in a city. It has to be at least 30 kilometers between the people. In the best case, about 150. What does ultra-high vacuum mean? We are dropping pressure from 12 to 15 orders of magnitude. 15 zeros. It's roughly 1 trillion times lower than the atmospheric pressure we breathe. And that's the level of isolation Rydberg atoms have to have just to survive. At this point, even the vacuum itself becomes an engineering nightmare. Metal walls, they give you gas. Metals itself look solid, but they have micropores which still keep some air, and they are slowly releasing this gas. And those several atoms evaporating from pores already enough to spoil everything. To avoid this, physicists use special tricks. For instance, they really bake the system. So first, all the vacuum chamber is warmed up, they heated to high temperature. It forces all the remaining gas from porous release, and then they cool it down again to a low temperature to suppress any remaining evaporation. There is actually another place where we can get those fancy conditions, the deep space. Somewhere between stars, the density of gas in the universe is that low that Rydberg atoms can form. And that's quite beautiful. To study those fancy atoms, we reproduce this outer space right in the lab. But there is another problem. Even if you remove all the molecules, you are still not alone. Each the object around is warm, and all the warm object glows. We are surrounded by a sea of invisible thermal radiation, and it's surely enough to demolish Rydberg atoms. For the regular atoms, the thermal radiation is just a background noise. It does not change anything. But for the Rydberg giants, it could be a catastrophe, because the gap between the high level and the ionization energy is that low that energy of thermal photon can literally demolish it. It gets ionized. For the Rydberg atom, 25 degrees Celsius surrounding us is not a sauna, it's a doom mount. It totally demolishes the state. So to see Rydberg state, we need not only a vacuum chamber, we need a frozen vacuum chamber. We need to remove all the molecules around and we need to cool down everything around. Then we have to shine a laser of a certain wavelength, not even one but a combination of several lasers of certain wavelengths. Only then the quantum state goes from the ground to this certain specific level. But why did they choose their specific levels? If it wasn't about just a massive size, what was they actually after? And why use rubidium, not the hydrogen? In physics, the transition from theory to experiment is always a game of compromise. Ironically, hydrogen is almost too perfect. Rubidium, however, is a perfect stunt double. It behaves quite samely to the hydrogen, having one lonely electron orbiting far away from the core, but it's dramatically easier to control. To control individual atoms, we have to use optical tweezers. It's a tightly focused laser beam that acts actually like a tractor beam. But trapping is only a half of the battle. We also need to cool them down and jumpstart their transitions, and that's where hydrogen totally fails the convenience test. Its heat transition lay in deep ultraviolet spectrum, and ultraviolet lasers is a nightmare, especially in the former times. Rubidium is, however, laser physicists' dream. Its transition lay in the infrared spectrum. In the infrared, all the lasers are well developed. They are easy to build, to tune, and exist already for a long time. Physicists choose rubidium not because it's fundamental, not because of its simplicity, but because they simply can't control it. So what's about principal quantum number? Why did they choose level number 50, not 1000? And the answer is obvious. Physicists were not aiming for the size, they were aiming for control, which actually matches for choosing of rubidium. States around number 50 are the Goldilocks zone of Rydberg physics. The atoms are huge enough to interact with the neighbors, to have a bigger lifetime. Beyond this point, binding energy becomes dangerously low, and as you understand, if an electron is detached, it's not a Rydberg atom anymore. Even the slightest disturbance is enough to tear the electron away. At the higher states, the Rydberg atom is too fragile. If it's not a size, what was the goal? It all comes down to a single word: control. Experimental physics is a constant struggle keeping the system from decay. It's like a plugged guitar string. It inevitably damps out, and then the atoms comes to the ground state. And in the ground state, it's not a Rydberg atom anymore. But the Rydberg atom gives us a counterintuitive advantage. You would think a weak bond would mean a shorter lifetime, but it's the opposite. As the electron moves far away, the decay slows down, and this buys us time. In the extended time frame, we can engineer interactions, we can manipulate the atom. So the Rydberg atoms are interesting for us not because of the size, but because we can manipulate it in the huge time frame. In the works which deserved Nobel Prize, the atoms were, though, quite huge, 125 nanometers. It was 1,000 times bigger than something you would call ordinary atom size. But the true power of Rydberg atoms is their endurance. It could stand up to tens of milliseconds. In scale of all the quantum mechanics, in scale of atomic physics, it's eternity. Thousands, even million times longer than everything you can reach in the regular atom. And when the level number 50 was reached, that's exactly where the real play begins. To manipulate such atoms, people could not use UV, neither visible light. They had to use microwave. In such excited states, the energy spacing between two levels was about 50 GHz. Electromagnetic waves with such frequency are not visible, it's actually microwave radiation. Ideas of quantum computer was done in the microwave oven, which was shined by lasers. And that's where giant atoms stops to be a part of scientific curiosity. They became one of the most promising frontier of quantum computing. A single atom effectively became a qubit. Unlike the regular bits where you have 0 and 1s, you have in quantum bit a superposition between 0 and 1. Quantum object as a Rydberg atom natively supports superposition. A real magic occurs in the architecture. Using optical tweezers, you can make 3D clusters of such Rydberg atoms, which will interact with each other, and the geometry topology of such system can be almost arbitrary. Using optical tweezers, we can make a certain precise arrangement. We can make a grid of atoms which is interacting. When these atoms are brought into proximity, they start to build quantum links, which are necessary to quantum computing. Today it's not about theory. There are already companies which are building quantum computers running on those exactly principles. Companies like UERA and Pascal. They are building machines which are powered by neutral and Rydberg atoms. And such schemes are advantageous in some senses compared to standard superconductive squid system. Because when you have superconductivity, you have to cool down all the circuit to quite low temperature, and it's really demanding. In this case, you have to cool down units of atoms. Using laser tweezers, there are surely problems, people struggling with it, but it's in general easier. And there is one more application which sounds like straight out of science fiction. Quantum spying, my friends. It's not like a three-body problem, it's not giant atoms are listening to your conversations. The idea is simple. Since the electron is far away from the core, the dipole moment is giant. The radius rises as a square, but the polarizability grows way faster, something like 7th degree. When the level is 50, atom becomes hypersensitive to all kinds of electromagnetic field. Okay, quantum spying is a bit too dramatic, but the sensor, based on those principles, must be incredibly sensitive. Size of the atom is defined by this expression, and there is another way to make the atom bigger. If using not n, then how? There is another way. We will not touch fundamental constants. Look at the formula of atomic radius. There are two things which are not that fundamental, which can be changed. They are mass of electron and also permittivity of the space nearby. And how can we change those fundamental constants? We must look not the electron in the free space, but electron in solids. When electron is in solid, permittivity of the space is changed, drastically changed. It's not 1 anymore, it's between 10 and 15, it's really a lot. When an electron propagates through a crystal, it interacts with all the electrons of all the atoms the crystal consists of. And strangely enough, it behaves this way, as it have had a different mass. The physicists call this mass effective mass, because it's not a real mass of the electron. It's like a mass which represents its activity. Inside a semiconductor, something remarkable happens. A conduction electron can pair up a hole which is positively charged. Together they can form a quasi-particle called an exciton, which behaves almost exactly as a hydrogen atom, but with a twist. In this environment, the electron feels much lighter, its effective mass can be 20 times smaller. At the same time, the material itself works like a magnifying glass. It makes electric force lighter, with the dielectric constant which 20 times smaller. Combined, those two effects blow size of the atom by 400 times. And that's just a ground state. Just like Rydberg atoms in vacuum, here exciton can be excited to higher states, and its size scales as n squared, allowing us to make really huge exciton. Such huge excitons are also called Rydberg excitons, samely to Rydberg atoms, and my colleagues studied them. Unfortunately, we cannot reach in the Rydberg exciton levels of 50 and above. As far as I know, limit is roughly 40. Meanwhile, the system itself is really interesting and promising object for the following research. Just imagine a huge hydrogen atom inside of a crystal. I wonder if it didn't yet deserve Nobel Prize. By the way, as far as I know, size of such Rydberg excitons reaches several microns, which is still giant. So what's the story of giant atoms? It's not just a fancy stuff from the lab. It's not a record-breaking scale. That's a story how people managed to build a piece of deep space right in the lab and control a quantum state of a single atom. It's a story of compromises, how we replaced hydrogen by rubidium. By making atoms giant, we did not just gain the size. We gained something way more important in quantum physics. We gained time. It allows us now to make a Lego-style quantum computer of giant atoms. Or we are getting hypersensitive quantum microphones. Rydberg atoms allowed us to control quantum world. And even if quantum spine or giant atoms is just a clever marketing, I'm curious of the physics itself, of the technology standing beyond. Don't forget to like the video. Peace and giant atoms to everyone, my friends.